Did you do your homework? Did you think about what I asked you to think about last time? Did you make an honest attempt at uh, writing down the for every vector space defining a Lie algebra on it? If you didn't, I'm gonna track you down. I'm gonna make you do your homework. So beware. Uh, okay. So let's think about let's go back to this table. There's one other thing that I wanted to say, and that is that well, there's a lot of other things I wanted to say, but a lot of science and logic and philosophy and maybe even art is about the duality of synthesis and analysis, right? So analysis, I want to take my objects, maybe they're groups, and I want to dissect them into like maybe smaller subgroups or quotients or something and break them down into simpler pieces in order to better understand the thing I'm dealing with. And then synthesis is doing the opposite, right? Taking smaller things and putting them together. So maybe if I have two groups, I take their direct sum. And so you should ask yourself about this analysis and synthesis, right? So as I already sort of pointed up above that there's like you should be thinking about what are sub-objects and what are things to quotient by um, as an example of analysis. But then what are things of like synthesis, right? So like for vector spaces, we have wedge things and tensor products, and we have direct sums, right? These are ways of putting vector spaces together. Groups have direct products, which are the same thing as direct sums. And there's also semi-direct products, if you've heard of those. So think about this. Like, what are ways that we could maybe put Lie algebras together? Of course, Lie algebras are vector spaces, right? So maybe some things that happen with vector spaces are also useful for Lie algebras. Okay, let's answer this question. Does every vector space have a Lie bracket? Is there a Lie bracket you can put on a vector space? Well, yeah. And remember, we want to be we thinking like mathematicians, we want to be thinking as economically as possible. Let's do the stupidest thing that we can, right? So if I need to satisfy this condition that all the vectors are zero, right? Well, every vector bracketed with itself is zero. What if I just did that with every vector, right? Like, what if I just define UV to be the zero vector for all vectors? Well, this condition certainly holds because the negative of zero of the zero vector is the zero vector. And the Jacobi condition certainly holds. Uh, because let's start writing it out. So like x y z bracket doesn't even matter what this thing is, right? This whole bracket's going to be zero plus, and you write out the other terms, those are also going to be the zero vector. And so of course that whole thing adds up to the zero vector. So this is great because now we have, it seems kind of stupid if these are the only Lie algebras that exist, right? Because then it's like, well, that bracket really isn't doing anything. But hey, it's at least we know that not only do Lie algebras exist, but there's at least as many Lie algebras as vector spaces. And so this actually gives us the following definition. A Lie algebra is abelian if, well, exactly this condition. So a Lie algebra G, I should say a Lie algebra G is abelian if for all x and y in G, the bracket of x and y is the zero vector. And why is this abelian? Well, so I want you to forget a bunch of examples that we have pretty soon, but let's go back up to the original example I had in the first episode of n by n matrices, right? We figured out that two matrices commute if and only if the Lie bracket, right, this commutator, the Lie bracket was zero. So you could imagine then that if you had some sub collection of matrices that all commuted with each other under multiplication, well, this might not be a group because those matrices might not be invertible, but it's still some sort of multiplicative structure. And that's a thing that we normally call commutative or like abelian if we're talking about groups, right? So that's sort of the motivation for talking about for having this definition as abelian, right? So we've showed that every vector space can be given the structure of an abelian Lie algebra. And so on top of that, this already starts to answer some of our questions, right? So what are commutative sorts of things? Or things about centers, right? That maybe gives you hints, since I already called something abelian, about what these other things should be, right? Or this largest commutative quotient, largest abelian quotient. Ooh, so what would you have to do? What would the thing have to be to quotient your Lie algebra out by in order to get some sort of largest abelian quotient of your Lie algebra? Things to think about. Theorem that you're going to prove, unless, I don't know, you tell me you're really, really stuck in the comment section, but I don't think that'll be the case. So let G and H be Lie algebras. Again, we're working over K, where K is either the reals or the complex numbers, such that they have the same dimension. And let's say it's finite. That's not important. Is it? I don't think so. Then if G and H are abelian, G is isomorphic to H, right? So basically, there's one way to make an abelian Lie algebra out of each vector space, right? Which intuitively is pretty clear, right? Because it's like you're this one overpowering definition of what that bracket does. What's an isomorphism of Lie algebras, you ask? Well, remember we talked about what a homomorphism of Lie algebras is. And as soon as you know what a homomorphism is, an isomorphism, some of you are going to be tempted to say, oh, it's a bijection. No. Remember that in general, for any sort of algebraic objects or any sort of category, a map, a homomorphism is an isomorphism if there exists a homomorphism going in the opposite direction such that if you compose, so psi goes from H to G, then phi goes from G to H. So this is the identity on H, and psi goes to the identity on G. Now you might say, why am I making a fuss about defining isomorphism this way? if I have a pair of maps that are inverses to each other, isn't that a bijection? Yeah, that's true. That means both of these maps are bijections. Okay, so what's the big deal? For example, in topological spaces, it's not enough for something to be a homeomorphism. So you can have a bijection that's continuous. So I'm sorry if you don't know topology, just ignore this example. But the point is you can have a bijection that's continuous, but you don't have a continuous inverse. And so you shouldn't really think of these spaces as being the same. Now, the thing is, it's true for vector spaces and for Lie groups, even. I'll tell you this now, that you do get the theorem that it's good enough if you just knew that phi was a bijective Lie group homomorphism. That would be enough. But you should prove that that follows from this definition. And why I say that is, again, because it's much more general to have this definition of isomorphism, right? It just works in more contexts. I just mentioned the example from topology where it doesn't work to just have a continuous bijection, right? And the other thing I like about this, I'm not a full constructivist zealot, let's say, but it's one thing to know, to give some sort of abstract proof that maybe, this phi here is surjective. I think it's so much better to say that to be able to explicitly tell me what the inverse map is. I think it's really nice to be able to have a particular isomorphism, say what that isomorphism does, and not only a particular isomorphism, but the particular inverse map. But that's just me. That's just my preference, if it's possible to give it in that way. Yeah. So let's begin. I'm going to be following Fulton and Harris here. And I thought I was going to go so long in this video, but you know what? It's late. I'm in the office and I'm tired and I want to go to bed. So I'm going to cut this one. Well, let's get started. The point is we're going to sort of do the analysis. We're going to forget that we know a bunch of examples, and we're going to start hunting for Lie algebras. And we're going to try and classify all of the Lie algebras that exist, right? So we're going to just sort of move up by dimension, trying to find a non-abelian one, and see what we can argue. So first off, there's in dimension 0. Well, we already talked about this. Did I talked about this with some students today, but I did. Yes, we did in the last video talk about the stupidest example. So 0-dimensional, again, you can prove, well, it has to be abelian, right? And so by the uniqueness of abelian Lie algebras, there's one abelian one here, and there's nothing else. There's just the 0-dimensional Lie algebra. Okay, what about 1-dimensional Lie algebras? Well, to that end, so suppose the dimension of G is equal to 1. Well, what does it mean to be 1-dimensional? That means there exists X in here such that, well, X is a basis. Hence, for all elements of my Lie algebra, I can find some scalars in my field, either real or complex numbers, such that both of these things are just scalar multiples of, y is equal to alpha x, z is equal to beta x that are scalar multiples of my field. And so if I look at this arbitrary pair of elements and I see what happens on my Lie bracket, well, that means that this is alpha x, beta x bracket. But the bilinearity says I can pull this scalar out in front, and it says I can pull this scalar out in front. So I got alpha beta times x bracket x, but my basic theorems on Lie algebras tell me that x bracket x has to be 0, the 0 vector. So this whole thing is just the 0 vector. So in other words, any pair of arbitrary elements in this Lie algebra has Lie bracket 0, and therefore there's a unique one-dimensional Lie algebra. Okay, up to dimension 2. Two-dimensional. So again, we know that we have a unique two-dimensional abelian Lie algebra. So suppose G is not abelian. Or rather, before we even really suppose it, we can play around with some conditions to see what would happen, right? But at the very least, we're supposing G is two-dimensional. So let xy be a basis for G, right? So now, if it were the case, and I mean, you can prove this using the same proof strategy we did above pretty easily. If x times y, if x bracket y were the 0 vector, then G would have to be abelian, right? So we don't want this, right? We want to hopefully convince ourselves that x times y can be a non-zero vector, right? So if that's possible, well, if G is not abelian and well, if G is not abelian, then the bracket of x and y is not 0. In this case, I claim that x and xy is a basis. Now, why am I doing this? Well, the secret is because I know how the proof works already, at least how I know how my version of the proof works already. Because the thing is, what we would like to do, right, is that x bracket y, whatever that is, because x and y themselves are a basis, we know that there has to exist scalars alpha and beta, such that x bracket y is alpha x plus beta y, right? Because they're a basis. And what we would like to do is maybe try and find nice conditions on these x and y. And who knows? I mean, maybe some things could be possible, right? Perhaps we're allowed to choose alpha and beta to be any complex or real numbers as long as they're not both 0, right? Because we're trying to avoid the case when this bracket is 0. We're trying to construct a non-abelian Lie algebra. So that's one thing. And then you could ask, well, if I make different choices, right? If I choose an alpha prime and a beta prime, Are those Lie algebras even non-isomorphic, right? Because now you start to think, wow, I can make all these choices for alpha and beta. Uh, but then probably if I can make all of these choices for alpha and beta, then like it could be that each choice leads to a non-isomorphic Lie algebra. Well, one thing I'll spoil for you now is suppose alpha was non-zero, right? Then if alpha was non-zero, I could scale x and y, right? Alpha inverse x and alpha inverse y. This would still be, oh, I was about to say something very silly. Um, uh, the what we want to scale by is 1 over root alpha. So this only works, of course, if alpha is non-negative. But then we could apply this argument to y bracket b. I'll leave that for you to understand. But if I scale both of these by the root of 1 over alpha, then this will still be a basis. And now if I take that bracket, right, because I can pull both of these out in front, this will be 1 over alpha times the bracket of x and y. And so that would be x plus beta over alpha y, right? So, okay, we can sort of cut down our space a little bit because probably scaling a basis, right, should not lead to a non-isomorphic Lie algebra, right? It's just some sort of choice of basis for the underlying vector space. Yeah, okay. But that still leaves some possible parameters for us here. Okay. So we would like still somehow to obtain some nice object. So what I'm going to do, like I said, Z, I'm going to define that to be the bracket of x and y. And I'm going to leave you with a claim. My claim is that xz is a k basis for G. And xz has a nice description. And a theorem that will follow from that is that there is a unique non-abelian Lie algebra of dimension 2. Okay, that's where I'm going to leave it. That's your homework. Next time, we're going to continue following Fulton Harris, and we're going to dive into an examination of trying to discover all of the three-dimensional Lie algebras, including, and I don't care what anyone else says, it's true, the most important Lie algebra in all of existence. 100%, hands down. Okay, that's for next time. I'll see you then.